today is the last, what is that? The practical class, because we have done with all the lectures, right? From 1 to 10. For the practical part, this is the last one. And today's session is actually very, very important because we are trying to, what is that? I'm trying to instruct you how to test for the qualitative type or categorical type of data, because so far I teach you only numerical values or quantitative type of data, how to test it. Yeah, as you see, for the quantitative type of data, we have numerous, we have so many tests. So we uh, uh, we sort it out, yeah, in which situation we can use different type of test, and we can select it suitable one for our data, right? What our data wants us, or even what we want from our data, right? So in order to answer to this question, we have to memorize all the tests that we have. And today's chi-square test is also not exception, because we have to also think from the perspective, so the chi-square, in what situation and how we can apply this kind of chi-square test, okay? So this is very important because, as I told you during the last time in the laboratory session, chi-square, Excel cannot do it for us, unfortunately. Yeah, Excel file, like we are from the data analysis, we are choosing several options, right? Several tests. Just we are commanding the Excel, and right away the Excel is doing for us. So you see that for the chi-square test for today's practical, why I'm saying that it's very important, because we have to do step by step by ourselves. Finally, we shouldn't be relaxed and getting uh, what is that, very comfortable with the Excel, right? Sometimes Excel also cannot do some task. So that's why one of the example, and it's very, very obvious from the today's session, that sometimes we humans also we have to do by ourselves. Okay, so let me introduce you to for the chi-square. If you remember from the session for the lecture, what did I say? We use the chi-square, and it's very powerful, yeah, because we don't need to really focus or stress on the numerical values. Maybe our test is want us just to compare, is there any relation association, uh, or maybe is there any agreement, yeah, between the two variables. Let's say, is there any agreement between the two variables? So in that case, we will not really take numerical values as it is. So we don't need to calculate for the descriptive statistics. We don't need to really care about what type of variation is there. How much is this variation? What is the standard deviation, for example, or standard error of the mean? Yeah, or we need to stress on the confidence interval, 95%, 99%? No, we don't need to really care about it when we are thinking of the chi-square. Why? Because we are just focusing on the categorical values as a frequency, right? So, how many people saying, yes, I will do online, for example? How many people say, no, I don't want to do online? And I will compare from the previous history, yeah, from the previous semester, students say like this. So, usually, I make a statement or I make a hypothesis. Usually, students say, yes for the online, yeah. So in this case I can compare from the previous already existed, already done by some kind of researcher, or already it is existed in our society, this kind of stereotypes, and I will conduct my observation. See, for the chi-square we have expected and observed values. So it's very easy, right? And if you remember the formula, I will show you later. Uh, Also, another one thing, that chi-square has two type of tests. The one is the goodness of fit between the observed and expected variables. Okay, sorry, the values. The second one is test of independence. Yeah, these two is very similar, but for the test of independence, in case we don't have expected values, um, we can actually calculate it. For the first one, the chi-square, the goodness of fit test, it's also very powerful and it's very simple to conduct it. Because we don't trust anyone, we don't trust on the society what they are saying, we would like to do by ourselves. So we already have expected values, we want to have observed values, yeah, and we will compare between these two. Not just comparing, we are seeking for statistical solution. We are making a statistical sense of this kind of observed values and expected values. How are they coexisted with each other? How are they agreeing with each other? Yeah. So see, in economical departments, for example, they do some kind of questionnaire test. So in most cases, they do this. They choose this kind of categorical test. Okay. So let's see. What is it saying? Now I will try to explain. I will start with the goodness of fit test. What is this? Okay, so let's say um, in Oman, we believe that in all overall in all hospital or overall in our population in Oman, we say that the proportion of the babies born it's 1 to 1. That is meaning 50% usually boys and 50% usually girls. Yeah. So is it true? Then I can just choose any random. What is that? The hospital they deliver babies, and I will start recording. Oh, I will just ask simple question from the nurses, from anybody, from the doctors, like how many babies uh, for the last 5 months or for the last um, we can't see anything. Abdul Malik. No, I'm. Do you see? This one is moving. Yeah, this one is moving. So soon I will share the Excel file. Okay. Here I'm talking about this one. All right. So how many? I will ask the simple question from the doctors or from the nurses. How many boys is born for the last 5 months or for the last 1 year, and how many girl in terms of gender? Yeah, how many baby girls born? And I will compare with what people believe. Yeah, by statistics. So let's say the ratio is usually 1 to 1. So it is a kind of 280 babies. Yeah, 280 babies. So half of them usually boy and half of them is usually girl. So I want to compare this kind of test. Let's see. I conducted my experiment and my observation is little bit, do you see? My observation is not exactly 140 of them is a boy. Only 128 of them is a boy and 152 is a girl. So I would like to test, yeah, because here I see the deviation is 12 here. Do you see that this much deviation? So it's not really like a error or this is the fact, right? So in that case, I want to test if this number that I recorded, is it fit to 1 to 1 ratio? Yeah, statistically, I want to make a sense. Like if you remember to the alpha significance 0.05, and in chi-square analysis, what I say, we also use chi-square. It has its own table. We don't refer to the t-test table, students t-test. We don't refer to the ANOVA test, which is the F table. Yeah. So chi-square has its own table. You see, it is also like similar to the F table little bit because it is one-tailed always, and the obtained value for the chi-square is always positive. So usually we test for 0.05 alpha significance. Okay, so I want to calculate and I want to make inference at the end, like at this 95%, I'm sure that my ratio is fit to what people say to that ratio. Okay, so here we have expected values, which was done by another researcher, and I have my observed values. Okay, so let's copy this one to the Excel file. Let's copy. So you can write here your student ID number. It is not sharing. Okay, good. So I have this data copied to the Excel file. Okay, and here I want to see how much deviation is there. In that case, I need to just deduct from one to another. Yeah. So completely like a 12 deviation. I can also write down the total number. Okay. Mhm. So you also copy it to the Excel file. Now we will start calculating it. Okay. Usually I like to write, let me see, observed and expected values. Okay, this one, copy and reverse it. Okay, I like to write observed on the column and expected also in the column, but in the row, I want to write down the each categorical group, yeah? So first group is the boy, the second group is the girl. Okay, I like to write this kind of because it is easy for calculation. Okay, you can also make like this because there is no difference. Yeah. So what I'm saying is here on this row, I will start calculating using the formula. By the way, which formula we are going to use? Do you see this formula? Chi-square equals to summation of, in the brackets, observed values minus expected values. Yeah. Multiply by 2 divided by, again, expected values. Okay, so let me copy this one just in case here. If you want to, yeah, great. Okay. So by using this formula, I just simply start calculating. So the reason why not this one, but this one, I like this way. Okay. And let me just highlight. So here I will calculate. So for the first category, for the boy, let's calculate it. I will open the bracket using this formula. Yeah, I have observed values minus expected values divided by, again, expected values, like this. And simply enter. So we got this value, right? So similarly, for the second category, for the girl, observed frequency minus expected frequency minus to the power of 2, multiplied by 2, and divided by, again, the expected frequency values. This is how we can calculate it. Okay. Mm. So we calculated for the second categorical group, which is the girl. Okay. So what is next? We will just simply summation, right? We have to adding each values to each other. So that's how we can write here I square. I square, actually it is the Greek symbol. It is not X, okay? It is chi. For the Greek symbol, this one, right? Insert plus chi square. Ah, very good. So summation. We can do two different way. We can put like this, and from the home we can do this one, yeah? From the home, from the right end, you will see there are options for the summation symbol. And from first, it will do like this. This is one way. Another way is equal sum. If you click 2 times, it is asking, give me your values. So I will do addition. So we will simply do like this. Halas. Done. So our chi-square value is 2.06. Okay. Yeah, this is our chi-square value. So now we need to bring chi-square critical value, if you remember. For that case, we have to what is that? Obtain our we have to identify the degrees of freedom. So in this case, our degrees of freedom is, what was that? One minus one. So it will be 1, okay? Because we have only two groups, the boy and the girl, two categorical groups. So in this case, we will just use, what is that? Here we have 2, so 2 minus 1, it is 1. So the simple way, actually here, we can use the chi-square table, which is from the, I will bring it to here, chi-square table. Let me copy. Okay, this is our chi-square table, yeah? So for the degrees of freedom, what we see is for the alpha significance at the cut point of alpha significance, 0.05 is 3.8. So we have here 3.8 for degrees of freedom 1. So what will be our statement, our inference at the end? Our obtained chi-square value is less than 3.8, right? So in that case, our, what is that? Let me write down here. The null hypothesis and alternative hypothesis. So what is it saying, our null hypothesis? There is the simple way, what we say, the observed and expected values, they're equal to each other. So another word is the ratio of 1 to 1, yeah, because we are comparing here by ratio. So the ratio of 1 to 1 is really true. It's true with my observed data. Or so in contrast, the alternative hypothesis, no, the ratio of 1 to 1 is not really matching with my ratio, right? So see, there are plenty of statements you can make it, and it's not a mistake, okay? So when I ask you to write down your, what is that? Your hypothesis, you can make it. You can make it in different way so that I will understand. what do you really mean? Yeah, we can say that we don't have a sufficient evidence to say that the true ratio, in this case 1:1, in the born baby population, um, the born baby population, the born babies population is different from the ratio that the researcher observed. Or simply you can say that observed value observed value is equal to expected value. So here is observed value is not equal. How can I find that not equal? Anyway, I will not spend time on it. Is not equal to observed is not equal to expected value. Expected value or ratio. Okay, so this is our alternative hypothesis. So in this case, we what we say, we have to accept the null hypothesis. We have to accept this one, yeah? Accept the null hypothesis. The null hypothesis. Hypothesis. Alright. Why? Because our obtained value of chi-square is less than chi-square critical value. Okay. I want to teach you another, not teach you, let me say, I want to know that to calculate probability level for the chi-square. As long as we calculate the chi-square obtained value, so Excel can also calculate the probability value. Only thing is Excel directly cannot calculate chi-square obtained value for us. Okay, I will teach you how we can find the probability value. If you are a little bit struggling to understand the values, obtained value, and comparing with the critical value, some of you feel comfortable, right? Some of you feel comfortable just by comparing the probability values. If probability value is more than the probability cut point value 0.05, you accept the null hypothesis usually, right? But the probability value for your experiment is less than cut point or rejection point of alpha significance of 0.05. In that case, you reject the null hypothesis. So here I will teach you how we can find the probability value for this situation. Okay, let's see. In that case, we will just simply call one command chi-square dot dist dot rt. Here is probability p value. Okay. So how can we? It's usually italic form. Yeah, probability value at cut point 0.05, 0.05. Okay. So chi-square. Do you see? There are some options appear. So just click the second one. CHISQ.DIST.RT. Okay, click twice. It is asking, give me your chi-square obtained value and give me your degrees of freedom. So in our case, our chi-square obtained value is 2.05 or 2.06, yeah, if you round off. 2.06, you can type it or you can just plug in that one, comma, degrees of freedom is 1. Degrees of freedom is 1. Close the bracket. Okay, close the bracket. Enter. See, the probability value here is 0.15, which is more than alpha significant of cut point 0.05. So we accept the null hypothesis. We accept the null hypothesis saying that they are in agreement. My observed value is not much deviating from the expected value, right? I have to also give my agreement with the expected values, so that the born babies in Oman or in other country, for example, where are you testing, where are you focusing on, depending on that born babies, usually the ratio for the born babies, it appears that 50% usually boys and 50% usually girls. And you already tested, yeah, if it's really true, by collecting some kind of your observed data. You see the power of the chi-square. So this is the statistically you're making sense. Statistically, from the statistical point of view. Okay, so this was the first example. And let's mm, similarly, let's do for the second example. Yeah, second example for your good practice. Let me do. So, uh-huh. So this example, what is it saying? This example is actually for the plant scientist. In plant scientist, for example, if you wonder why when I go to the market, there is a flower is pink color and flower which is having red color, white color, because people prefer, right? So according to the people preference, the breeders or plant scientists, we try to get as many variation in color as possible, right? Because we want to sell it. If I will produce only pink color, I will not sell that much that I have diversity of colorful flowers, for example, in the market. So from the plant scientist is a big challenge because we need to understand genetics of the color, yeah, which gene is associated with the color, for example. So usually what we find out that usually what is the color here? Colored means purple color, pink color, even black color, yeah, it is dominant, or that is meaning the frequency for the black or for the pink color usually is much more, twice, triple times more than the white color. Okay, this is actually scientifically it is proved. Yeah, for example, if it's a purple color, is over dominant over white color. That is meaning the frequency usually the 75% to 25%, 3-to-1 ratio. This is scientifically it is proved. So I want to test this kind of belief. Yeah. So some researcher made a collected. He crossed two plants. He crossed it, and the offspring, the generation, showing some kind of patterns. Okay, if he see 1,000, nearly 1,000 plant, and from 1,000 plant among, he collected some kind of data for the purple colored flower and white colored petal or flower. Okay, so the ratio is 3-to-1, and it is, what is it, the one researcher, he is actually very famous in plant genetics, Mendel. He collected the frequency 696 purple color, 232 white color. So I also want to test it, yeah, as a plant scientist. I want to test it, and in my case, 705 is for purple color, and 224, it was actually for the white color. So the deviation is 8.2. So deviation is 8.2. I also, what is that? I also have to make a total number is exactly the same. Yeah, I cannot make more or I cannot make it less. Exactly same the previous researcher did, 929. So what I say here, so let's reverse it. Let's make it like this way. Yeah, transpose. So I want to make grouping like this way. Yeah, observed value for the and expected value in columns, and for the categorical groups in rows. Okay, so what I say, because it is easy for me, for you even to calculate it. So here, using the same formula, yeah, using the same formula, we can calculate it. Let's do it. Open the brackets, observed value minus expected value, close the brackets. You can put this symbol to multiply 2, 2, and the division to expected again. Okay, enter. For the second categorical group, which is the white color, open the bracket, observed minus expected. It's very easy task, yeah? It's very easy. And again, expected. You can repeat after me or you can do by yourself. Enter. So, summation, what I say, we can use from home and this symbol, yeah? Summation symbol. On the corner, you see? And the first option is summation. You can do this way, or you can simply equal symbol, sum. So it is asking, give me your values, I will do it for you. So I will just plug in simply these two categorical data's value, okay? But I have to close the bracket, enter, that's it. What happened? Okay, so I like to do like this way, not so many digits. After point, I like to keep only 2 digits. So this is my chi-square. .39. So here also similarly, degrees of freedom is only 1 because we have only 2 categorical groups. So here I will teach you again how we can find it if you don't feel comfortable with the obtained value of the chi-square, and if you don't know how to make if you're hesitating, what would be your conclusion, okay? So if you're comfortable with the probability values, I will teach you again. Let's call for the command chi, the second option, do you see? Chi sq dot dist for distance dot rt, okay? This one, second option. So it is asking, give me your chi-square obtained value and degrees of freedom. So our chi-square obtained value is 0.39, comma, degrees of freedom is 1 only. Close the bracket. Okay, done. So both of them are inversely correlated actually. The chi-square value is less than 3.8. Probability value is more than 0.05. See, they're inversely correlated. So in both cases, what we're gonna do, we accept the null hypothesis. Yeah? We accept the null hypothesis here. This is our overall statement. Sorry. Yeah, we have to accept the null hypothesis because our chi-square obtained value is much more less than chi-square critical value. Got it? Yeah, very easy. Or even our probability value is more than cut point significant alpha, which is 0.05. It's much more than we have to accept the null hypothesis, saying that there is no, I mean, there is agreement. Yeah, there is agreement between observed values with the expected value. Or we can say that, what is that? We can say that we don't have sufficient evidence to say that the true ratio of 3 to 1, yeah, in this case 3 to 1, in the plant population is different from the ratio that the researcher observed. So I didn't find any difference what researcher observed and what I observed. There is no difference. Okay, so this is my null hypothesis. On the contrary, the alternative hypothesis, I can say that there is a difference. There is no agreement between observed my value and expected the previously existed or established value. There is some difference. Yeah, they are not in agreement. So I have to deny it. So I have to reject the null hypothesis. See how simple it is. How simple it is. Okay. Remember that I want to say that here groups we have only color white. We can also have some kind of no color, transparent, and we have kind of some values. So in that case, we also do chi-square. Only thing is summation, and then we have to summarize. We have to adding up all the values for each category. Okay. So depending how many categories we have, so we have to calculate for each separately, like here, and also at the end we can summation and we can get the chi-square values. Then we have to also pay attention to the degrees of freedom. So here I have some values, then it will be 2 minus 1, sorry, 3 minus 1, it will be 2 degrees of freedom, yeah? The more get, the more degrees of freedom will also increase. The more groups are added, the more degrees of freedom will be also increased, right? So there is no restriction. Our categorical data, it cannot be only 2 groups. It can be 3 groups, it can be 4 groups, it can be 5, and so on and so forth. Okay. In this point, you have to be wise. Okay. So this all we have done chi-square of what is that? The goodness of fit. Yeah, I will write it down here. Chi-square goodness of fit. So always remember goodness of fit. Now, I want to also teach you how to do also test of independence. Okay, test of independence is very interesting also, very interesting, and you don't need to stress if you don't have, for example, observed values. And also you need to pay attention to the raw data you have. Okay, so for example, in your lab notebook, you see that the left hand and the right hand. Should I let me stop presenting? Let me share this lab notebook. Okay, so in your lab notebook, you see this kind of example. So here, what is it saying? As I said before, in the lecture time, there is one very interesting example. For example, the people who, because in society, usually in our population, we have people who uses most of them, right? Who uses the right hand. And there are also people, some particular people who uses only left hand. So the researchers were thinking that maybe this is the, the brain structure, because we have the right sphere and the left sphere in our brain. Okay, so we were hypothesizing that the people who use the right hand, they always use also the right eye. yeah, because in our symmetrical face, we have two eyes, two hands, yeah, something like this. So the right-handed people only uses the right eye when they are targeting on something. So usually what happens is when we are targeting on something, we usually close one of the eye, if you notice that, right? For more focus. So the researcher hypothesizing, so the right-handed people are associated using only the right side of the eye. And similarly, the left using hand people, they associated also using usually the left eye. Yeah. So they, what is that? They collect this kind of data. They collect this kind of data. So do you see the left hand and left eye? So this kind of design we usually call 2 by 2 design. 2 by 2 because we have groups not only in the row, we also have groups in the column part. So it is column-wise row or row-wise column. Okay. So the chi-square, what is it saying, is much more powerful than what we might think. So in this kind of example, we have groups, categorical groups for the column. We also have categorical groups for the row. So this kind of design is 2 by 2. It can be 4 by 4, depending on how many groups we have. Yeah. So in this case, only 2 groups for the column, 2 groups, 2 categorical groups for the row. So this kind of test, because we are seeking for association, we call it test of independence. Yeah, test of independence. So let's copy this data to our Excel file, okay? And we will now do test of independence for the chi-square. Allow me. Okay. So let me paste my data here. Okay. Move this to here. Ouch. So the formula we use for the test of independence, it is same, but we also have extra formula. Okay. And another thing is we only have observed data. We observe our data and we need to calculate our expected data. Okay. How we can do if we have only observed data? Yeah, because we believe that there is expected data also. And to make it more simple, chi-square can solve this kind of issue. Here, let me write down. I have only observed data that I collected, yeah, and I want to compare with the expected data. Or somebody did already this observed data, and you want to test it for the stereotypical established belief, yeah. Observed data. Good. It is very interesting. Mhm. So let me do the design. Okay, so here is I calculated, for example, here total values. So only focus 2 groups, 2 categorical groups on the column, 2 categorical groups on the row. So this kind of test design usually 2 by 2, okay? 2 by 2. It can be 3 by 3. It can be, what is that, 4 by 4, depending on how many groups you have. So remember, the more groups you have, the degrees of freedom will also increase, okay? Degrees of freedom also, like in this table, then you have to, for example, if you have degrees of freedom, you are testing for 6 groups, 6 categorical groups. But for the test of independence, we have to calculate which one? We have to remember degrees of freedom, how to calculate it, yeah? How is it? The row minus 1, column minus 1, and multiply between these two, right? Okay, anyway, let's go back to the observed value, how we can calculate it here. So, this one is 2 by 2, so we only have observed value. Observed value, how we can calculate expected value? This is the big question, okay? Expected value. For that, this formula come to us to resolve this kind of issue. Do you see? Row total and column total. 43. But we need to keep in mind we have two groups. So for each of them, we have to calculate it. Let me this one copy here, and for the left eye, okay, we copy just this one too here, yeah. Okay, so let's calculate it. For the first categorical, is left hand and left eye. The total is 54. 54. Should I open the brackets? Let me try without the brackets. Column total. For the left eye is this one, yeah, 137. Let me write it down for you to understand. 137. It's better to open the brackets. And divided by grand total is 400. Okay. Left eye with right hand. 20. Oh, sorry, it is not 27. Here is 54 because total. Okay, 54. Sorry, 54, not 27, because it is grand total, row total, column total. Enter. Right. Easy. That's why I highlighted in blue. Okay. Similarly, let's calculate for the second category, which is the right eye and left hander. Very easy. So 54, oh, let me open the bracket. 54 multiply right eye with the left hander. Right eye total is 200 divided by 400. Right. Now I will go to the second category with the right hand left eye and right hand is the right eye. Okay. Yeah. Open bracket. So the total is 346 multiplied 137 400. Perfect. And for the last one left is right hand for the right eye. Okay. Open the brackets. 346 multiply 263 divided by 400. Perfect. You see, this is how we are calculating our expected value using this simple formula: row total multiplied column total divided by grand total. That is why we have to first make a calculation for the total values for each category with association with the second category. Okay, and after doing that, we can simply use these total values finally for the test of independence. So here I simply summation. Okay, here also summation, and here also summation, here also summation. Perfect. And here again summation, it should be equal to what we have for the observed values. It should be equal. Okay, perfect. So the next step, we are not done yet. We are not done yet. Okay. We have to what is that? Summation of all this. Okay. Now we have to use the formula for the chi-square. This one we need to use it. Yeah. Formula for, we have to use now the actual formula for the chi-square. So how we can do it? In order to make it more simple way, let me see, we can actually deviation. We can actually calculate the deviation. So from the deviation, we simply can calculate the chi-square. It's not simple, but how can I say? It takes time, you see, for the chi-square, especially for the test of independence. One. So using for the deviation for the right hander and this one, we have to calculate the deviation. So deviation will be 27 minus 18.495. Okay, for the right hand, 27 from the observed value minus expected value, 35.545. Enter. All right. And 110 minus 118.545. Okay. 236 minus 127.9. Okay. So we calculated the deviation for all of them. Surprisingly, it is same. So we don't need to calculate here totals. Okay. So we see that this much deviation is there. This much deviation is there. We highlight it. So we calculated deviation also. So from the deviation now, we need to calculate the chi-square. Where is that? We'll copy this one. Now we will calculate using this formula. From the deviation, we can do it. So open the bracket. So our deviation for the first left eye and left hand is 8.505, yeah? 505. We have to square into 2 divided by this one, 18.495. For the second category is the second one, second group, summation. So this time minus 8.505 squared to the 2 divided by 35.05. Okay, plus. I will open the bracket again. 118, right? Sorry, it's minus again 8 point. Yes, just a minute. I cannot now. All right. Square it 2 divided by 118. And the last one, plus again, I will open the bracket. 8 point square to the 2 divided by 220.495. This is it here. Using this formula, from the deviation, I just square it. Yeah, from the deviation, as for the expected values, observed values, minus, like this, let me see, 6.87. Perfect. So this one, I will just leave it to you. If you haven't done, just try to understand the strategy. How did I do you see from here? Escape. Yeah, this one. Okay, I hope that everyone is done. Now, let's find the degrees of freedom. So in this case, we need to remember c minus 1 multiply to rho minus 1. Rho minus 1, okay? So what do you think? C minus 1 is 1. Rho minus 1 is again 1. So the degrees of freedom here, in this case, it is 1, yeah? So similarly, let's find the probability value, this one. Once we obtain the chi-square obtained value, it is very easy. It is very easy. Chi distance, this one, yeah, second option. Chi sq dot dist dot rt. So our chi-square value is 6.87. Degrees of freedom is 1. So this one. You see? 0.08. almost 0.09. Perfect. Oh, sorry. I just want to make it. So here, on the contrary to the goodness of fit, our chi-square would be, we have to be a little bit careful when we are thinking, when we are testing for the test of independence. Okay, for the test of independence, actually for the null hypothesis, we say that I dominance and handedness. Handedness means if you are either right hand or left hand, they are independent. They are means independent means people can use even though they are right hand or left handed. It's not necessarily they have to associate, they have to link with the, if they are right handed, with the right eye. If they are left handed, with the left eye. Yeah. So the alternative hypothesis stating that eye dominance and handedness are not independent. Not independent means they are depending on each other. So the eye dominance, if you are using the hand, actually the hand usually we mostly we distinguish people right hand and left hand, right? Not from the eye. Okay. So the hand actually it should be the hand is dominating, but for brain it comes to the eye. So that is why it is saying eye dominance. Yeah, eye dominance. So we use the right when we are targeting on something. We use the right eye. So in most cases, those type of people who using the right eye for the targeting, they usually right-handed people. Or those people who are, for example, for the targeting with the left eye, they are usually left-handed people. So see, in this case, what we're gonna do? We have to reject the null hypothesis, right? We have to reject the null hypothesis. We have to reject it. Why? Because our probability is less than 0.05 cut point, and similarly, in regard with also the chi-square obtained value is less than 3.8. Yeah, 3.8 from the chi-square table, we get this 3.8. 3.8 is our chi-square critical value because our degrees of freedom is only 1. So that our obtained value is more than 3.8. So in that case, we automatically reject the null hypothesis. We automatically reject the null hypothesis. So I hope it's clear. Just here what is challenging, how to calculate. The chi-square, you need to really pay attention. So why I calculate deviation? Because it's much more similar. Yeah, because here is the squaring them. Squaring them. That is why. So the deviation squared minus expected values for each category with the each associated category. Okay. So I hope you copy all what I have done here. You memorize it. The power of chi-square for the categorical type of data. Finally, we come to the position of understanding what I can do if I have only focusing my data to be categorical data. If I'm treating my data as a categorical rather than the numerical, rather than the quantitative, yeah? If I'm having qualitative type of data, what should I do? What kind of test I can apply? So no stress. Here we have chi-square and the simple formula. By using the simple formula of chi-square, we can calculate it. But we need to distinguish. Is it kind of a goodness of fit test? Yeah, goodness of fit test or test of independence. Test of independence. Okay, we need it. Test of independence. So we have two type of testing. Either it can be used as goodness of fit, where we have both the groups observed values, both the values, for observer group and for the expected. In contrast to the test of independence, we only have observed value. How we can calculate from the observed value the expected value? As I teach you here, we have to remember this formula: row total multiplied by column total, column wise, yeah, row wise. We are calculating with the use of that by the dividing to the grand total. Okay, so using this formula comes us to help how to do step by step. And finally, we can use the chi-square actual formula. That is why Excel cannot do it for us, because we need to still understand our data. From our data, we want to test for the goodness of fit test, yeah, or for the test of independence. That is why Excel will not do it for us. It can be in two categories, but I don't know why they didn't include the two categories, like one-way ANOVA, two-way ANOVA. But the good thing, the probability value can calculate for us the Excel, but we have to give the feed for the command as long as we type chi-squ.dist.rt. We have to feed our obtained value for the chi-square. That's how we can obtain probability value. If we are doing manually by hand by using the calculator, it will be very hard for us to calculate the probability value. Okay, so that is why the both of the values we can get it from the Excel, and both of the values we can paste it to our table and to show to our audience. I have this and I have this chi-square obtained value, and as well as probability value to 100% to be sure that you have done everything correctly. Yeah, everything is correctly. Okay, so we have done chi-square analysis. Please do your homework and submit it by Thursday evening, because Thursday I should be asking by Wednesday evening, but since most of you are stressing, yeah, and you are not completing your task, I will do extend it for Thursday evening. Please now complete your homework from 6 to 9, 6 to 9, okay? And also do at the laboratory manual, there is some kind of example. There is some kind of example. Let me show it to you. Here we have done everything, right? Everyone has done here. I will just stop my presentation. Let me open WebNote. Okay. Allow it. At the end of your laboratory notebook, you can see there are revision exercises. There are 14 different of the revision exercises. For example, here, what do you think the chi-square question look like for the practical exam? For example, number 4. Number 4 is obviously it is chi-square test, because we see here 4 categories, and this is test of independence. Yeah. Because this could be your observed value. Where is your expected value? You don't know. So, and this is column wise, 3 by 1, 2, 3, 4. So 3 by 4, 3 by 4 type of test of independence. So there is also a goodness of fit example. Goodness of fit example, do you see this one? Number 8. This is also chi-square. This is also chi-square, yeah? Because we have observed value, we can calculate from the observed expected value. Okay? Another, okay. I think 2 different type of chi-square is given here. So please pay close attention and also practice by doing the revision exercises. So this is it for today. I hope you adopt the skills for calculating the chi-square test. If you have any question, please ask me now, because later everyone is busy. I'm also busy, and you might be struggling to find me or to catch me. Yeah, please. No question?
Doctor, I have a question about the p-value, which is in chi-square.
Yes, please go ahead. What is your question?
I use another formula, which is
Yes.
chi-test. It's not depending on the degree of freedom. It's depending on just the expected value and the observed value. So if I get the degree of freedom wrong, I will not get the p-value wrong. Could I use it?
See, let me test it. Chi-square, the first option, yeah? Chi-SQ distance, only this one.
No, not the first one.
Oh, which one?
Chi-test.
The last one.
Yes.
Last one is asking actual range and expected range. Yeah, this is also can be used. Actual range and expected range. So you can just plug to the range for this one and expected range. Same. Yeah, same. You can use it, Amna.
Okay, thank you.
Yeah, because some people confuse. This is also a very good option if you find out the chi-test, the last one. But you need to know which one is your actual test and which one is your expected. Which actual meaning here the observed, right? The observed range and expected range. That's it. Good. Yeah, this gives the similar same result. You can use that option, no problem. Any other question? No? Okay, thank you for your participation. If you have questions, just you can ask me whenever you meet me, or you can just email me. Yeah, but I don't promise that I'm going to respond to each and every of you. So better to come to my office and ask me the questions. Okay, bring your notebook. Compile your all question in one note. Don't do it one by one. Okay, and ask me at once. This is my suggestion, please. Thank you so much for this journey to take me for the biometry. I hope you get what you really expecting. Yeah, your observed and expected was matching. I hope so. In the future, remember, for the statistics, there are advanced statistics. So this will be very handy if you know already what kind of test in which situation to apply. So please get ready for the practical test. If you are do successful in the practical test for your rest of your life, you will be appreciating yourself and your knowledge that I have learned these skills, because this is now for the rest of your life. It will be useful and it will be no change there is no significant change will happen in the future. We are using this for 50 years, for 50 plus years already, more than nearly to 100 years. So this is confirmed. And always remember the theoretical part and also the practical part equally. Okay, thank you so much.
Doctor,
right.
I have another question.
Yes, please, Amna, go ahead.
In the lab final practical, should we sort our data from the lowest to highest values, or it's not important? Only
It
it's
depends.
important
It depends
finding
for
the
the
median.
descriptive statistics. If you are trying to find the mode or median, then you have to sort out your data, right? But for the significant test, it's not really matter. It doesn't really matter if you sort your data or not. And sometimes sorting is also good, so that, for example, for the regression and correlation analysis, you want to see if you have a lot of data, you want to see the outlier, too much gap, variable to variable, sample to sample, for example. So in that case, you can easily spot. But if those variable, big gap numerical values if you have 100 samples, it is very hard to spot. So in that case, sometimes we usually sort, yes, from minimum to maximum.
Okay, Doctor, another
But for my
question.
exam, you don't need to sort it out for the significant test. Yes, please. Because we have very small data, 5 to 10, 15, maximum 20, 25. Yes, please.
Okay. Do we need to read the manual, the first theoretical part?
Manual, first theoretical
The
part.
lab manual here, the first theoretical part in
The laboratory notebook?
here.
Or
There is the theoretical part here. Should we read it for the practical exam?
no, this is for your understanding, right? Some of the students, they were absent for the lecture time, for example. So in that case, they can just introduce themselves with the brief introduction and review by looking at this kind of manual. That is why.
Okay, doctor, in lab 6, the part 3, they are asking about what car would you buy?
This is personal question.
I chose the first one because it is less than the other in the time that it breaks.
Yeah, it is a personal preference. I mean, what you have observed, yeah, by testing, because we are testing which one is more compatible. So it's a personal preference. Yeah.
Okay, in regression, should we insert the graph, the x and y scatter plot, or just it is in the correlation?
For the regression analysis, you have to do the scatter plot. Yes. For correlation, is actually scatter plot is not needed.
Okay.
Yeah, but for regression, you must do it because you want to see how the linear line, the best of fit line, is fitting in the scatter plot diagram.
And in homework 8, I didn't understand the last questions.
Oh, by the way, for the homework, it is about regression analysis, right? Regression analysis. It is little bit comprehensive task for the homework for the regression analysis. I will send you the manual how to do it. I will send it to you now to everybody. So just follow this manual, okay? Because here, as you remember, for the regression analysis, we have to do ANOVA test. We have to do ANOVA test, whether we like it or not. So by using ANOVA test for each and every, we have to categorize group by group. For example, here we have so many treatments, and we also have no treatments. So this kind of problem, actually, it is done by, it can be solved by ANOVA. So that is why you need to understand. So in order to answer to the question for each intercept, for example, for the rate, for how many regression analysis you are doing in this particular case. So it's a little bit comprehensive. So I will send you the manual how to do it, and you can get some idea how to fill out this what do you call it, this table. Yeah.
And the last the final question, yeah, this one.
Finally, this one.
Yes.
What is the probability if no difference in the rate of disease progress between varieties? So here also from ANOVA table, the probability value you need to copy and paste. So I will give you that manual and you will understand. I think here I have also given some kind of a guidance. Probability for 3 or 4 times of ANOVA you will do separately, or you can do simultaneously. It's actually depending on your capability and understanding, because we have one way ANOVA, we have two way ANOVA. You can make it factorial even. It is, there is no restriction. So any probability value you get for one way ANOVA you are testing or two way ANOVA you are testing, that probability value you need to paste it in here. You need to insert into here. Okay.
Okay, doctor, in lab 7, when we can determine when it is significant correlation.
No, I think 7 is significant correlation. Significant correlation, right?
Yeah, it's depending if the R value is negative or positive.
No. The correlation is significant or not significant. Remember what did I say here? Here for correlation, we have to ask from the t-table to resolve this issue. If our correlation value is true and it is significant, so we need to apply that the last formula given for how to test for significance of our correlation values, coefficient of correlation. So we are checking for the validity. So it is asking for, is it valid or not? And you know how to do it, right? There is a formula. Degrees of freedom. And from the t-table, we get our t-critical value. We compare with the t-obtained value. And based on that, we will make our decision. Is it significant or not significant?
Okay, another question also in lab 7.
Mm-hmm.
They are asking what is the best estimate of the value of P? How can we determine that?
No. Best estimate meaning the just cut point, the rejection point, you got 0.05 or 0.01.
Not depending on the R?
In question, or sorry, homework 7, you say?
Yes, this one.
Here is what is the value of R?
No, the last one, doctor. What is the best estimate of the value of P?
Yes, here for finding the T critical value. For finding the T critical value, you estimated using the 0.05 for two-tail test. Or some people, they use for 99% confidence interval. So in that case, confidence interval, what is it? The confidence, 0.01. Some people say highly significant value, 0.001. So in your case, if you choose 0.05, just tick on 0.05. That's it. You can actually compare. In case of 0.001, what would be? Is it still significant or not significant? So based on that, you can make a decision which one to choose for the rejection point, 0.05, 0.01, or 0.001 even.
Okay, in lab 9, when we accept the null hypothesis,
The
so there is no
chi-square
association between
in the
the value.
chi-square.
Yeah,
For which case? For the goodness of it?
no.
For
For
test of independence?
yes.
Test of independence, just refer to my Excel file. What did I say? It is on the contrary. For example, let me paste it in here from the Excel. Paste it. You see, for example, here the eye dominance and handedness are independent. It is in case of, just remember this one, these two words. Independent means null hypothesis. Not independent, they are not independent means alternative hypothesis. That is why we are testing for independence. So for testing for independence, the null hypothesis is always independent. The alternative hypothesis is actually dependent on each other. They are not independent. That's it. This is for the test of independence, but goodness of it, it is different. Yeah. They are in agreement, they are not in agreement.
Okay, thank you, doctor.
You're welcome, Amna. Very good questions. See, all the students should be like this, I wish. Unfortunately not. And they come at the end of the finals crying to me, I didn't expect this mark to get. Well, it's not depending on my, I don't know, my ability. I try my best. So depending on you, on yourself. Yeah. So please be very, very how can I say, focus, and after do what is required from you. But for doing is different. If you have gained the knowledge that I have provided to you, you are there is a probability that you pass the exam. But if you are not ready, if you didn't take any my advice, then there is a probability that you might fail. So please ask questions, be active. Even for the homework, yeah, even for the homework, because now it is depending on you based on how you are doing homework. No more question? Okay, you are free to go. I have another class to prepare. Okay, all the best for your coming exam. So this Thursday we will do practical final exam, inshallah. Okay, I will circulate the email to you. Please submit your homeworks. Start submitting now as soon as possible, and I will send you the manual for how to do the homework number 8.